All right, well, welcome everyone. I am JJ. Let's tackle an example problem. So we're doing a moment of inertia problem here. We're just asked to find Ix, our moment of inertia about this x-axis for our object shown. Our first step in here, we know for moment of inertia, really what we're working towards is we're probably going to have to use the parallel axis theorem on this. The parallel axis theorem tells us our moment of inertia about any axis I want to take a look at equals my moment of inertia about the centroid of our object, I bar, plus the distance in between these two axes squared times the area. So if I'm dealing with that, I'm going to have to break this up into pieces, and then I can start trying to apply this into each individual piece and just add it all up at the very end. So if I'm tackling this, I would say, well, I have a rectangle in here. I know how to work with rectangles. I put our table in here, kind of the three pieces I'm going to work with just to help this, but our rectangle, I'm going to call shape 1. I have a triangle on the left here. Let's call that shape 2. And then our last one is I have a full circle in here with a radius of 2 centimeters. Let's call that shape 3. Shape 3. 3 pieces to work with means I have to apply this equation 3 different times and just sum it all up at the end. So let's just go through piece by piece in here. My I1 should get me to, so I'm saying my moment of inertia about the x-axis for just shape 1 in here is the moment of inertia about the centroid of shape 1. Well, let's give me that Ix prime column in here. Remember, as we're looking at this table, we have equations for if our object sits on the axis of interest and a more general, what's our equation about the centroid? This first column, the moment of inertia about the base, very rarely actually gets used for everything. It's kind of a unique situation in there. This column on the right, along with the parallel axis theorem, is almost always what we want to use. If you're ever unsure, use the second one and the parallel axis theorem. I'm going to say my I1 is my moment of inertia about the centroid of shape 1. Well, that would be base times height cubed over 12. My base of that shape is, we're given 3 plus 9, so 12. The height of this, base times height, 3, 6. Base times height cubed over 12. Then we have to add in our distance between the centroid of shape 1 and our x-axis, our centroid of the object and the axis of interest, squared and multiplied by the area. So plus that distance should be, really, if we think about centroids, this is the same thing for our x-axis here. It's just, what's our y tilde variable? What's the distance from the x-axis to the centroid of the object? That's different if we're looking at a different axis in here, but for just a general x-axis, we could approach that as our y tilde from centroid. So plus my distance from the x-axis to the middle of a rectangle. Or is just my h over 2. I have to first get up to that. So 5 plus my height divided by 2, 3. 8 squared times the area. And the area should be 12 times 6. Times 12 base times height 6. Or this is 4,824. We're in centimeters. Centimeters to the fourth. Don't get hung up on what a centimeter to the fourth is. Nobody inherently knows what a distance to the fourth is. It's a really important engineering property for us, though. Loosely, it's telling us how resistant is this to bending. But just embrace that you're not going to understand a distance to the fourth. Your head isn't going to wrap itself around that. But I have I1. Let's just keep going with that. I2 should be, well, now I'm working with that triangle. And I'm going to do that same equation here. My moment of inertia about the x-axis for shape 2 is the moment of inertia about the centroid of shape 2. Well, I have that. That's base times height cubed over 36. The base is 6 centimeters in here. 6 times my height would be 4 plus 3 plus 3 plus 5. That total height is 15. Base times height cubed, 15 cubed, over 36. Plus, again, I need a d squared a in here. So it's my distance from the x-axis to the centroid, my axis of interest to the centroid of shape 2. Well, the centroid of a triangle measures 1/3 of the way in. from our 90-degree corner. We're given that h over 3 in here, from the 90-degree corner. So I need to first go up to that 90-degree corner, that's 15, and then I come back down towards the x-axis. So I'm going to subtract out a third of the height, minus 15 over 3, or this is just 10. But d squared, don't forget to square this, times the area. And we know the area of a triangle is 1/2 base times height. So 1/2, my base is 6, my height, we've used it before, is 15. 1/2 6 times 15. Or I2 ends up being 5062.5. 5062.5 centimeters to the fourth. And then I just have one last piece to work with. I have that full circle in there. I am going to treat that like it's a positive area for right now. We know we'll subtract out the end. If we start trying to make it every areas and pieces negative now, it almost always leads to problems. Just treat it like it's positive. My Ix3 should be, well, my moment of inertia about the x-axis for shape 3 is the moment of inertia about the centroid of shape 3. We're given that, pi r to the fourth over 4. So equals pi times the radius is 2 centimeters. Pi times 2 to the fourth over 4. Plus d squared a. So it's my distance from the x-axis to the centroid of my full circle. Centroid of a full circle is just the dead center of it. So from the x-axis, I go up 5, 8 to get to the middle. So plus 8 squared times the area here. Pi r squared. Pi times 2 squared. This one's going to get me 816.81 equals 816.81, not centimeters, not inches, centimeters to the fourth. And then I just need to combine the three of these to get to a single answer statement coming out there. My total moment of inertia for this, Ix, should be, well, shape 1 is positive, so Ix1. Shape 2 was positive, so plus Ix2. Shape 3 was negative, so we'll just subtract it out, minus Ix3. Or my Ix is going to get me 4824 plus 5062.5 minus 816.81. Minus 816.81. All together, we're going to get here that my Ix, my answer for this problem, is 9,069.69 centimeters to the fourth. Again, if you are in statics working through these, all of the application for this probably is going to come in later classes. Just get in the habit of being able to calculate these. You're going to need this down the road in a lot of follow-up classes. Figure it out now. You'll be thankful later. But hopefully this was a useful video for us. If it was, hit those like and subscribe buttons. Stick around, watch more videos. Let's get you in A with JJ.